Unit 5. And rational functions, just an introduction to limits. In Unit 5, we're going to investigate rational functions. We're going to rewrite those functions in hyperbolic form. It'll match your parent graphs from Algebra 2. And then we're also going to take a look at a concept called a limit. That will be later in the chapter. But first, we have section 5.1.1, where we will mainly talk about direct and inverse variation. The unit essential question, how do you determine the limit of a function? That will come up much later in the unit. The lesson essential question is how do we apply direct and inverse variation? To start, we have problem 5-1. Problem 5-1 is very similar to what we did in chapter 1 with the ViewTube activity. However, in chapter 5, we're going to change some of the parameters. If you remember the ViewTube activity from day 1 of Precalc, back when things were easy, we had view tubes. Everybody had tubes of the same length. We stood at various lengths from the wall, and we measured the width of our view. What you notice there, your independent variable being the distance from the wall, dependent variable being the width of view. As you moved further from the wall, your range of view got wider. As you got closer to the wall, the range of view got more narrow. That is an example of direct variation. As x gets bigger, y gets bigger. X gets smaller, y gets smaller. This chapter, we're going to be doing something called inverse variation. So what we're going to do now is we're going to establish a set distance from the wall that you will stand. And the tube length is going to change. We're still going to measure that width of view. Now, what you will notice is that as the length of the tube gets longer, the width of your view gets a little smaller. And as the length of the tube gets shorter, the wider that you can see. So picture yourself looking right now with no tube. Those of you that have peripheral vision, you can see pretty much 180-degree range of view. However, if you had a tube that was quite long, that range of view ends up being a function of the diameter of the tube that we're going to explore in class on Monday, section 5.1.1. So, we're going to have a graph. I need you to set this up a while so you are ready when class begins on Monday. Go ahead and set up your grid. Again, doesn't have to be a Picasso, should not be a kindergartner. And what I'd like you to do is go ahead and label that graph, count off units, and what we're talking about here is this is going to be the length of our tube. And this is going to be our range of view. I'd also like you to go ahead and set up a T-chart for yourself. That T-chart, again, independent, dependent, x comma y. This will be width, and that'll be view. We're going to need that come Monday. Now what's going to happen is I already have the tubes pre-cut, pre-labeled with set lengths. What you will do in your teams is you will choose a few different tubes, probably 6 different tube lengths. You'll record that tube length in your, that's length, not width. You'll record that tube length in your T-chart, and then you'll measure what that width of view is. Make sure the same person is always looking through the view tube, so that way the same height is being used every time. And what we're going to notice here is that as the length of our tube gets longer, our range of view is going to get smaller. As the length of our tube gets shorter, our range of view is going to get larger. Okay, and that's going to give you a hyperbola shape from Algebra 2. So this will prepare you a little bit, having a blank graph and a blank T-chart so that we can get right into it on Monday. 5-2 talks about some definitions here. This should go into your toolkit. It gives you an entire math notes box on direct and inverse variation. So I want you to take out your toolkit. I want you to label one box direct variation. And I want you to label another box inverse variation or indirect variation. They each have an equation. Alright, directed variation is an example of like a linear function. Say something like y equals k times x, where k is your constant of variation. Label that in your toolkit. Inverse variation, you'll notice, is y equals k divided by x. K is still that constant of variation, except now we're dividing it by the x value. Alright, this is algebra 2, mx plus b. This is a little different. This is algebra 2, we're talking about a hyperbola. Now the key factor there, and some notes for you to jot down, is big X here equals big Y, and vice versa. However, down here, in an inverse variation situation, we would have big X equaling what? Small y. That should be logical to think about. If you're multiplying by an x value, you're making something bigger. If you're dividing by an x value, you're making something smaller. That's 5-2. There's some extended notes there in the math notes box. I need you to write down everything that you can to help you remember direct and inverse variation. The main idea is, however, being what these two equations are. You need to know those. We will use them often. The last class problem is 5-3. Let's take a look at that. In 5-3, it gives us an example of direct and inverse variation. The problem tells us, suppose y varies directly with the square of x. Y varies, y equals, directly tells us which equation to choose with the square of x. The square of x describes the function. So part A says express this relationship using k as your constant of variation. So for part A, which equation am I choosing? I'm choosing k times x because it's direct. It says y varies directly. So y equals k times direct times with the square of x. That is x squared. There is your general equation. Part B asks us to solve for the specific solution for k when y equals 3, x equals 2. So part B, we have some givens. They tell us y is 3 when x is 2. Well, what's the only variable we do not know at this point? The only variable we do not know is k. So let's plug in for everything that we know. 3 equals k times 2 squared. And solve that equation for k. We will find out our constant of variation for this specific problem. So we have 3 equals k times 4, which means k equals 3/4. However, you're not finished. The problem asks you to express the equation when you're finished with the constant of variation included. So our final answer there would be going back to our original equation and substituting 3/4 for k. Now we have an equation for that variation problem. Moving on to part C. Part C then asks us to apply our equation. So the newfound equation y equals 3/4 x squared is what we're working with. And it asks us to find the value of y when x is -3. So I just substitute x equals -3 into that equation. Y equals 3/4 times -3 squared. Should be quite simple. -3 squared is 9. So we have 3/4 times 9, which comes out to be 27/4, which, yes, probably is the best way to write that. Keep in mind as we move forward in math, improper fractions are a blessing. We do not want mixed fractions. We do not want decimals. Now that decimal could be rounded off, so I wouldn't take off any points on a test for that. But when you do come across a decimal that cannot be rounded off, remember, again, from way back in chapter 1, improper fractions are the best. There is a very brief presentation of what direct and inverse variation are. I will see you in class tomorrow.